What am I doing today? Today, I'm going to talk about option pricing. Today is going to be a mix of math and finance. It's our third lecture. The first one was a lot of business considerations. The second was a lot of math. Today is a bit of both. So today we're going to be talking about pricing theory. And I want to do that by focusing on one example that's going to be with us for the rest of the course. We're going to take a lot of advantage from that example. It's this one here. Okay, don't read. Listen to me for now. Okay, imagine let's play a game. Okay, who wants to play a game with me? Do you want to play a game? What's your name? Kevin. Yes, I remember Kevin. Okay, let's play a game. I don't have a coin. It's in my bag somewhere. Okay, I have a coin. Let's say I flip a coin. And if heads shows, I give you $1. If tails show, I give you nothing. Yeah? Okay? And don't forget, for a few weeks, including today, we're not aiming to make money. We want to understand financial markets from the perspective that everybody works for free. Okay? If you start bringing fees when you're beginning, it's very complicated. It's easier to add fees when you know how things should work for free. So we're going to play that game. We don't aim to make any money. If I flip a coin, it's a good coin, 50% chance of heads, 50% chance of tails. I have no particular interest in doing anything. We work for free, right? How much would you pay to play that game? 0.5. 0.5. Okay, so at 0.5, we think it's a fair price. Sometimes you win, meaning I give you $1, you pay 50 cents. Sometimes I win. Okay, I give you nothing. Right? The idea is that over a period of time, as we play more and more and more, we more or less break even. That's the concept that you've learned in probability. So you'll understand that, yes? I flip a coin, 50%. Okay, great. So let me express the same game in a different way. Let me express the same game in a different way. Let's say that I flip a coin, but instead of giving you $1, if heads shows, what happens is I flip a coin, and if heads show, then the price of a certain asset, stock, house, something, goes up. Let's say from $1 to $2. Okay? So it's a random event. It has a 50% chance of happening. I flip a coin. If the asset price goes from $1, so if heads show, goes from $1 to $2. And if tails show, it goes from $1 to 50 cents. Okay? Go with me? So I'm not playing games now. There's a certain asset, and it has a stochastic price tomorrow. Today is $1, but tomorrow it has a stochastic price, which could be $2 or 50 cents. And we say it's 50-50 probability, right? Yeah? Okay, great. So now comes the new game. Who wants to play a new game with me? You. Your name?
Zach.
Jack.
Zach.
Zed.
Zach.
Zach.
Like Jack is that?
Zach. Okay, Zach. Yes. There's a lot of echo here, and getting the nuance of consonants is difficult. Even sometimes getting the nuance of vowels is difficult, but vowels are easier. So Zach, we're going to play a game, okay? And the game is as follows. I'm going to forget about the coin now. I just look at the asset price, but it's the same thing, 50% chance of going up, 50% chance of going down. If the asset goes up to $2, I give you $1. If it goes down, I give you nothing. Okay? Now the question is, how much would you pay to play that game?
50 cents.
50 cents. Great. Okay, so you pay 50 cents for that game. Let me do the following. So you and I are playing. You give me 50 cents. And before tomorrow, this is happening tomorrow, right? So before tomorrow, what I do is I go to my bank. Can you be my bank again today? You're going to be my bank for the rest of the course. Is that okay? Yeah. And I forgot your name. Cheryl, that's right. So I'm going to the Cheryl Bank, okay? And I say, Cheryl, can you lend me some money? Can you lend me, I don't know, let's say 20 cents. Can you lend me 20 cents? Yes, good. So you lend me 20 cents. Now with the 70 cents I have, I go and I buy 70% of the stock. Okay? You're following me, yes? I'm doing a transaction now. I'm forgetting probabilities, I'm doing a transaction. Remember the world of the make-believe where math lives and the real world with transactions where is money. So I buy 70% of the stock. So if the stock goes up, my 70 cents, my 70% of the stock is worth $1.40, right? I give you your dollar and I return your 20 cents. Let's say there's no interest beating. It's easier that way, okay? I return your 20 cents, and then I have 20 cents left. Okay, all right, so interesting. What happens if the stock goes down? Of course, I lose. The 70 cents that I invested has become 35 cents. I have to give you nothing. But I give you your 20 cents, and I have 15 cents left. Something is wrong. What's wrong?
The option isn't priced correctly.
That it's the conclusion. You're right. Yes, the option is priced incorrect. But what's wrong is that I'm making money. I'm not supposed to make money. For a few weeks, we're not supposed to make money. Right? So no matter you give me 50 cents, no matter what happens, I make money, extra money, either 20 cents or 15 cents. Right? You're happy, you're the lender, I give you the money back. I don't, you want to add interest to that, I can modify the argument, let's say without interest for now. So what's the conclusion? The option is priced incorrectly. That would be but why? I mean, how did you get to the 50 cents?
I just took the expected value of the payoff.
You took the expected value of the payoff. You did the same thing that Kevin? You see, 5 minutes I already forgot. So the same thing that Kevin was doing, right? So Kevin and Zach live in different worlds, or not, okay? Let's ignore the pricing of the option. That is just an academic statement, okay? What is really happening here? I want you to understand the significance, the financial significance of this. Do you understand? Yeah, you see that? By the way, who knew this already? For whom this is a surprise, you've never seen this paradox, so to speak. Raise your hand, come on, if you've never seen this paradox. This is new to you. I want to know, if it's not new to you, then I can assume you know a few things. Okay, so, all right, so this is new. So this paradox is new to you. So what's going on? It's like, isn't this shocking? Yeah?
If you include the price of the option in the payoff, then you would do.
If I include but now you're being very academic, okay? I will be academic too. I'm gonna be very academic. In fact, today, if I have time, I'll prove a theorem for you. The only theorem I will prove for you in this course. But before we go there, I need you to have the right intuition about what's going on.
I think the kind of lending is a different sort of like payoff associated. So by introducing the lending, it's now like kind of a good deal for you. I think.
Okay, well, we're gonna have an answer, okay? And the answer is gonna be given by a theorem, believe it or not. Okay, it's like we're discovering the laws of gravity. We say, oh yes, of course the apple falls from the tree. We know exactly. But it's as if now the apple goes up instead of down. No? Don't you find it counterintuitive that he's paying 50 cents, same game as Kevin, same probabilities? And by the way, if you're thinking, oh, let's play more times, play more times. Every time we play, I'm gonna make 20 or 15 cents. You're gonna play 1,000,000 times, I'll be rich. Right? So over time, it doesn't correct, it gets worse. I make even more money. Okay?
What about 25 cents?
Sorry?
What about 25 cents?
20, okay, so if you pay 25, I'm not going to play because then I will lose all the time. But see, what you're doing is you're looking for a price now. So before I continue and before we see the answer, there is an answer, okay? The price is 33 cents. It's exactly right. It's $1/3 of a dollar. That's the exact price. But before I show you the price, let me tell you something that happened. And I want to tell you a story. And like all good stories, there's a bit of an exaggeration in it, but only a little bit. The moral of the story is true. And the answer is this. In the 80s, 1980s, okay, 1980s, by the way, that's when I was doing my thesis at Princeton, okay? I was doing my thesis in math. I was a mathematician. I did my thesis in mathematical physics, it so happens. If you go to the physics department at Princeton, it was much, much bigger than the math department, much, much bigger. And most people were doing their thesis in solid state physics, particle physics, okay? That's when you have, there's just string theory, all these wonderful things. That's when physicists realized that differential geometry was very useful to understand particles. And it was an explosion of activity and papers being written and PhD theses being written, but there weren't enough jobs for all of those physicists. So it was the same at Princeton, MIT, Harvard, everywhere, okay? So you do a brilliant particle physics thesis and then you have to look for a job. Guess where they ended up? Wall Street. Okay, so well, I was doing my thesis in quarks and here I am at Wall Street. Okay, what happened is this. This theory that we're talking about today was done in the 70s. Okay, so this thing that we're going to be discussing today is from the 70s. But most people in Wall Street did not know about it. And they continue to, this is where the exaggeration happens. They continue to pay 50 cents for these options, like Zach, right? And then these particle physicists, they saw the theory we're going to see today. They said, wait a minute, this is worth 33 cents. So what do you think they did? They told Zach, no, you're paying too much. You don't do that, okay? This belongs to in the part of the course where people actually make money, okay? But you can imagine, right, in the 80s, what do? I say, Zach, you want to play again, and again, and again, and again, right? What would you do? Well, this is arbitrage, yes. But so when you fight arbitrage, what do? You write a paper, or what do? Do
you sell options to Zach?
Yeah, as many as possible. I call you every day. I say, hey, bad luck today, and I call everybody here. By the way, you want to buy? Maybe I try to sell them for 49 cents. Who would buy this for 49 cents? Now I have a lot of buyers. If I offer this for 49 cents, we'll think this guy's stupid. He's losing 1 cent per transaction. He's going to go broke. And I'm making money all the time, right? Okay, so this is, I'm exaggerating a little bit, but this is, in a certain sense, how the derivatives market grew and grew and grew. Okay, and the 80s was the right time. We're going to see a little bit of history later on when I tell you about the history of financial markets. And the 80s is the period that came after the 70s, and the 70s was the period of tremendous world chaos because of the oil crisis, the de facto rivalry between the United States and Iran in the 70s. Okay, so derivatives were everywhere. Everybody needed protection. So I said, well, sure, yeah, you pay 50 cents, great. I give you 50 cents protection against the stock going up. And every time I do that, I make a lot of money. So they became very profitable traders. In fact, option pricing in the 80s was called particle economics. Because no one understood what they were doing, but they were making money, so there must be some interesting economics these guys found. Again, a bit of an exaggeration here. All right? So this thing we just discovered with Zach's trade is not a small thing. It changed the course of history. And of course, this is the beginning of arbitrage-free pricing, something that Steve Ross had already discovered 10 years earlier, but no one knew. The reason is that the level of sophistication that you need to understand all of it was just not there. Now, anybody from economics here? You're from economics, okay? So all economists know this now, but not back then. Not back then. Okay, differential equations, systems of equations, they were not so well known to economists. Game theory was not there yet. It was already there. John Nash already written his paper years and years ago, but it was still not mainstream in economics. It was not mainstream in mathematics. There was no course in mathematical finance at Princeton. I didn't know that these things existed, right? So there is a radical change introduced, and this is the best example that explains it. That's why we're going to milk this example so many times in the rest of this course for many, many things. Okay? So the first thing we must learn today, is beware of probability. Pricing options, pricing derivatives, pricing things with probability is very dangerous. We just saw this. You're going to lose money all the time, and you're taking probability. So how come, by the way, footnote, how come probability is a requirement for this course? By the way, I'm trying to dispense with the prerequisites for this course, but...
Well, we still would have to use it, just a different measure, right?
Well, okay, so as I mentioned to you, yes, you know where I'm going, right? So as I mentioned to you, really, 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 math is your superpower, all of yours, okay? So if your math is weak, make it strong, because that's your superpower. And this is going to show here. So it is not that there's anything wrong with probability. No. There's nothing wrong with probability, okay? What's wrong is that we just don't know enough, okay? We are led to believe what is in front of our eyes. And we know, you know that mathematicians like to always question things, and right? And so what can we question here? What kinds of things somehow would you find strange? Let me try, instead of pricing the option, let me try to price the stock, right? So if the price of the stock is $2 tomorrow with 50% probability and 50 cents with 50% probability, what's the expected value of the stock? 125. So if the stock is priced incorrectly by probability, why should the option be priced correctly? That would be weird, don't you think? Interesting. So that we just said that it will be weird that the option happens to be 50 cents. Now we are saying the exact opposite of what we said earlier. At least we're learning something. We see that this paradox, you don't have to come up with an option price. It already is there when you try to price the stock, right? So if the probability really is 50%, then what should the price of the stock be? That requires a calculation. If the probability is 50%, the stock price would be 125. But if it's $1, what's the probability? What should the probability be? Let's now question the probability. Maybe the probability, sure, is 50, but maybe it's not 50. Maybe something else.
So then it should be a third for 0.5, or two-thirds for 0.5 and 1/3 for $2.
Yes. Do you all see that? Do you all see that? Let's spend some time on that. Okay? How do you do that? You're a genius?
You just compute the difference between like 1 and 0.5, and you compute the same.
Let me say that differently. You solve the system of equations. Yeah. Two equations, two unknowns, right? Or actually, if you want, it's really one equation. If P is the probability that it goes up, and Q is the probability that it goes down, P plus Q is 1, right? And 2 times P plus Q divided by 2 is 1. That's what you did in a fast way, but that's what you did. Are you all with me? Please, if you're not with me, if for whatever reason you now think of, you're hungry and you forgot it, tell me, I cannot lose you, okay? I lose you now, I lose you forever. And this is so easy. I cannot lose you. If I lose you, raise your hand and ask me, what did you just say? I was thinking of a friend. That's fine, I'll tell you again, okay? I cannot lose you. P plus Q equals 1, 2P plus Q times a half equals 1. That's the equation we're solving, right? And what's the answer? I know you know equations, I know. But what's the answer? You said it, you cannot say it again. Everybody else, please say it. What's the probability that it goes up? What's P, probability of going up? 1/3. Okay, I need everybody to say 1/3. There you go. Okay, that's good. Like a choir, 1/3 exactly. And the probability that it goes down is? There you go. Perfect. Great. Okay. Now I feel like Benjamin Zander. Finally. Good. So, what is that 1/3, 2/3 combination? Now, what is it? It prices the stock correctly, but maybe someone will continue to say, no, it's 50%. Probability goes up is 50%. This is what analysts do all the time. They say probability of stock price, because the iPhone is not selling so well in China, it's going to go down. And that's what people do, right? They give you probabilities of events. What we're doing here is we're calculating, it's called the market expectation of the stock going up, okay? People in the banks, they love to do this so much now, that I'm sure maybe you followed, we had the World Cup, the soccer World Cup, which is followed. There were people that were implying the probability that I don't know what country wins the World Cup from market prices. I mean, now people take this to the extreme, right? But you can read many probabilities. For example, what's the probability that Trump is going to win? People were doing this, looking at financial markets and calculating the probability implied by market prices that Trump's going to win. I don't know if did you see that? Yeah? It was there, the probability. Well, markets price probabilities all the time. The probability that maybe you saw today, they say that the Bank of Canada will likely increase interest rates by 25 bips. Now, that's very close to your heart because you're doing assignment number 1, right? Guess why people think or say it's likely the Bank of Canada is going to raise rates by 25 bips? Because it's in the bond prices. Very much like what we're seeing here. So suddenly this thing is not new. We just never thought about it. Yes? Great. Okay. So, there's one thing missing in this thing I'm telling you, okay? There's one thing missing, which I have not convinced you that probability is real in any way. I have not convinced you that the price, by the way, what's the price with the probability that you mentioned? Is 1/3, right? Okay? So it's 1/3 times 1, that's the payoff, plus 2/3 times 0. Then the price of the option would be 1/3. But I know I have not convinced you that I gave you evidence that it probably is 1/3. In fact, if I asked Zach, how much would you pay? Now you'll probably say 1/3 of a dollar, right? That would be my guess. But I haven't given you proof. I've given you evidence, but not proof. I want to give you proof that it's 1/3. Okay? And this is what I mean by proof. So, Zach, let's play. If you give me 33 cents, yes? 1/3. Then I go, Cheryl, you lend me 33 cents. Good, I have 2/3 of a dollar. So I buy 2/3 of the stock. And I wait. Tomorrow, we meet again. The stock went up to $2, what happens? Give you your dollar and, oh, 33 cents left. Here you go. The stock goes down. It's like nothing for you. And then, oh, 33 cents. Here you go, Cheryl. No one made money. Now I've convinced you. Now you know the price is 33 cents. Now we learned something. Yes? See, with probabilities, I could not convince you, and I should not be able to convince you with probabilities, even if they are implied probabilities. Why? I just told you, don't do probabilities. So if the 50-50 is misleading, the 1/3, 2/3 could be misleading too. Right? Okay. There is a theorem, maybe I'll do it today, that will tell us that in this context, the probability that prices the stock will price everything. Okay? Everything, not just this option, everything. And what does it mean to say that it prices everything? Well, there is a very nice corollary of that theorem, which is that every option like this can be replicated. This thing I just built is called a replicating portfolio, which is, I'm replicating the option by taking a loan and buying a stock. That's a replicating portfolio. Why? Because the option happens to be exactly the same payoff as this portfolio we just built. We did that last week with the bond forward contract, remember? So we haven't done anything today. I just wasted half an hour of your time. We did exactly the same thing. I just dressed it up differently. Don't worry, we're going to do this over and over and over again. Okay? We're going to do things that may look different, but they're all the same. And of course, after we do these 3, 4, 5 times, then I should better change topics because that part would be very well understood. Okay? Yes? All with this slide. This is something that I want everybody to understand extremely well. I'm calibrating that everybody understood this very well. I cannot go to the next slide until this is perfectly understood. Okay, let me see if it's understood. What will happen if now Cheryl decides to charge me interest?
Without interest, then the amounts of the average, right? We should,
Yeah, so I'll have to change the replicating portfolio, okay? Which is a little bit messy because, oh, exactly how much? And then I have to go and change and then come on. But the replicating portfolio, I hope you realize, is another system of equations, right? How did I decide how much loan I take and how many stocks I buy? How did I decide that? Well, with hindsight, I knew it was 1/3 and 2/3, and you saw that it worked. But if we change the parameters, if I change that $1 by $1.10, I change the bond price, which is what I'm really trading with you, from $1 to 90 cents. How would you get the replicating portfolio? Same thing, it's a system of equations. You just have to make cash flows match, just like we did last week. How do you realize that? If you had not realized that, then you had not fully understood this example. So if you changed all these numbers, you do the same thing, except now you can maybe not do it in your head. Maybe now you need pencil and paper. Which is to say, oh, well, I don't know, let me see, I buy X stocks and I borrow Y from Cheryl. And then when I buy the stock, it's at whatever the price is, $1, $1.10, I don't care now. I'm writing my equations, right? And then I get an answer. I get the replicating portfolio, I get the price, I get everything. And it's all because of a system of equations. Yes? Now I know you are with me. I'm convinced. But let me tell you something else now. I'm not sure if you realize this. Your assignment number 1 is the same thing. You are building a replicating portfolio. A coupon-bearing bond is replicated by a portfolio of zero coupon bonds. And you're trying to price each of those zero coupon bonds so that the price matches the coupon-bearing bond. You see? So assignment number 1 is the same thing. And what we did last week is the same thing. So I could have taught these 3 weeks entirely differently. I could have started with the theorem, which I will prove today, and then everything else is a consequence. And then I'll be done in an hour. And then I will know you understood nothing. I could tell you that theorem, you will know, and I can examine you in the theorem, and then I'll ask you this, and you will know, I don't know, 50 cents. Right? Now you have the intuition, and then we will see the theorem. But it's important that you link the two. And from now on, never ever price something because of probabilities. Unless they are implied probabilities, as we will see in that theorem. Okay? Good. So I think, I have a very distinct feeling that everybody understands this well. I care about this so much, I want to check the chat, see if there's a question on Zoom. Okay, everybody has to understand this, even if you're on Zoom. Okay, what does S you're reading the equation. No, I didn't say, I think I told you don't read the equation. Okay, I said just listen to me. So I'm gonna answer this question now. There was something else in the chat? Okay, no, there was nothing else in the chat. Okay? That was just only there for reference, because now I'm going to present this in a financial way. This game I played with Zach is now, what is it? Is a call option. I'm not sure if you know what a call option is, but this is a very, very commonly traded financial instrument. It's called a call option. It's just that people rate this differently, people call this differently. So now that we understand this, let me start giving you financial terminology that you also understand, okay? So I'm going to write the payoff of this option as follows. I'm going to write it as S minus 1, S being the stock price, so that's the answer to the Zoom question. S is the stock price. I'm starting to give names to this. And you will see that little plus symbol next to the bracket. I don't know if you've seen that before. It's very commonly used in finance. That is it's a function value, which is the value of the number in brackets if the number is positive, and 0 if the number is negative. Is the positive part of that number, okay? Maybe you've seen it before, maybe not. That's okay. You know what it is. It's very conveniently written like that. We're going to use that very, very often. Okay? And you can check that that's exactly the payoff of the game I played with Zach. 2 minus 1 is 1, and a half minus 1 plus is 0. So that exactly describes the payoff. It's convenient because if you change the number, the stock goes instead of $2 to $3, right? Then I'll give you 2, and it's expressed by the same thing. Of course, the game changes, the payoff changes now. So this is what a call option is. Call options are important because several reasons. So let me talk about finance now, real finance. Okay, why are call options like this important? Because what these call options do is they describe a financial transaction which is very common. Okay, let's say who would play this game? If the stock goes up, I give you $1. If it goes down, I'll pay you. That's stupid. No, it's not stupid. It's stupid if you say it like that. Not if you write it like this, because what there's a financial way to re-say or restate or say differently what I just told you, which is I give you the option, that's what's called an option, not the obligation. I give you the option. A futures contract was the obligation you had to buy. Remember? But today you have the option, not the obligation, to buy that stock for $1. That's why it's written like that. See, if I give you the option to buy the stock for $1, that means that I will pay you the difference. That's where the difference is there. Right? I give you the money, the difference that you would need to buy the stock at whatever price it's at. You see? The consequence of giving you S minus $1 positive part is that I allow you to buy the stock for that price. That dollar price is called the strike price. If S is less than the strike price, you have the option, not the obligation, to buy the stock for $1. You say, no, I don't want to buy a stock which is worth 50 cents for $1. That's what it's called an option. And that's where the payoff is zero. So you see, the payoff is there to reflect the value the option will give you so you can exercise the option. That value is called the intrinsic value. All of these are financial terms. They're not written in my notes because I don't care very much for them. Okay? I care about your thought process. How they are called is not important. If there's the strike price, it's not important. But it is the strike price. Okay? $1 is the strike price. Yeah? So something important is coming. Don't get now thinking, oh, when is the theorem coming? No, forget about the theorem. I don't care about the theorem yet. There's more I need you to learn. We're learning about 2 decades of finance with this example today. So 2 decades is in an hour is good. Yeah? So give me an hour, okay? I'm not done yet. So I allow you to buy the stock for $1. Why would anybody do that?
You can use it to shield risk, but if you have like some sort of like a investment already in the industry or some connection, then you can kind of you can buy an option or you can sell an option. So in case it goes down.
Yep, you can do that. However, let me say that this is not the way or the reason they were invented. Let me tell you why they were invented, okay? So I need to play a game with someone now. I'm looking for the next CEO of the Bank of Nova Scotia. I'm not sure if you know, Bank of Nova Scotia had a big issue looking for a CEO. They just hired one, okay? I think it started on February 1st, I think. Let's pretend that the CEO has not been hired yet. And let's say I'm the board of the Bank of Nova Scotia and I'm looking for the next CEO. Yes? Okay. So who wants to be the next CEO of Bank of Nova Scotia? Do you want to be? Yeah? Okay. What's your name?
Yancy.
Jancy. Oh, yes, of course, you told me, yes. So you want to be the next CEO of the Bank of Nova Scotia?
Yes.
Okay, you're hired, okay? Let's negotiate your salary now. How much you want to get paid for that?
$500K. $500K.
Oh, it's like, he's
year.
cheap. He's cheap.
$2 million.
2 million, okay, fine. 3 million, okay, whatever. How do bank CEOs get paid? You have to get ready for this because I want all of you to become bank CEOs, okay? So you have to learn. This is the part of the learning that I know I'm motivating you when I say that. Okay, so yes.
A lot of the compensation is stock options.
Stock options, exactly. So let me tell you how to negotiate if you get that offer from Bank of Nova Scotia, okay? If so salary, something small, let's say $5 million a year, okay? But where you really get good compensation is what is the Scotiabank stock right now? Can someone check for me? I have a lot of friends at the Bank of Nova Scotia, okay? If they're watching this video, sorry, it's a joke, okay? $69.52. Let's say 60. Okay, So stock price of Scotiabank is 60, okay? So let me tell you, now I'm your advisor, okay? I'm your advisor for the salary. Negotiating the salary is always very complicated. So now a salary, give me something, you know, like 5 million, something, you know, something that, so it's worth my time to get out of bed in the morning, 5 million. But this is what I want. I'm making this up, okay? I want 1 million stock options on the stock price of the bank with a strike of 60. I'll be generous, 65. Okay? What does that mean? If I hire you as the CEO of the Bank of Nova Scotia, and apart from your meager $5 million a year salary, I give you 1 million stock options with a strike price of 65.
It gives incentive to profile the CEO.
Yeah, you are the CEO. What's the job of the CEO?
Increase the company value.
Is maximize the company value. So the job of the CEO is to make that $60 stock be as expensive as possible, 100, 500, as much as you can. That's the job of the CEO, right? So then I should compensate you as a function of how high you can make that stock price go, right? If you go from 60 to 100, the shareholders will love you because they make 100, huge return, right? So I think shareholders will be in favor of giving you stock options because you make money when they make money, right? You see that? Yeah? That's how stock options were originally introduced. For management compensation. CEO, but same thing could be for the CFO, for the people whose actions can really change the value of the firm. You pay them with stock options. It's almost free. If I pay you 5 million, that 5 million comes from my pockets, from the pockets of the shareholders, right? Because I'm reducing shareholder value by $5 million for the whole company. But if I pay you with stock options, it's like you work for free, right? Right, okay, so this is how stock options were introduced. And actually, one of the people who got the Nobel Prize for some of the theories we're going to see in this course is Myron Scholes, a Canadian from Timmins, Ontario, got the Nobel Prize for some of this. And in his Nobel Prize speech, which is on the website, on my website, you can see it, it's one of the papers that I included. He tells the story of how he got into this. And I think it was Wells Fargo, a bank, hired him on a consulting basis to figure out the value of these stock options. Because when the bank is hiring someone, they say, well, yes, sure, I'll give you 1 million stock options, strike price of 65, and yeah, that's great, and I hope you make it 100, and then I make money too, but how much is that worth? How much is that worth? When the company gives you those stock options, how much are they worth? And it has implications because maybe there's tax on that. And then you have to, how much? So I'm giving you something, right? And I want to know how much that is worth. That was the question, how much is that worth? Well, now we know, right? Of course, it's not that the stock of the Bank of Nova Scotia can go from 60 to 70 or to 35 and that's it, right? It's a bit more complicated than that. And the stock options are stock options that you can typically not redeem, say, for 5 years, right? Because you're there, I said, oops, something happened. Quickly, I sell my stock options and I'm out of here. I become the CEO of Bank of Montreal now, right? Now you have to be there for a period of time. Make sure that the shareholder value has been consolidated, right? Okay, so this is how they were invented. This is how they were treated. And these are the reasons, the drivers for that. But there are many other applications of stock options, okay? Let me, to complete, I really want to, like I said, milk this slide as much as possible. Let's say that this example I have here is actually not for a stock. Let's say that $1 is not really a stock. Let's say it's a currency. Okay? Let's say it's a currency. What's the exchange rate of the Canadian dollar versus the US dollar right now? 1.3. Yeah, let's say it's 1. I think it's a bit more. Let's say it's 1.3, right? Let's say it's 1.3. What most Canadian companies, they share the same risk, which is that most Canadian companies, they have their income in US dollars, but they have their expenses in Canadian dollars. Why is that?
You do a lot of business with the United States, maybe they export, maybe they buy things.
Exactly. So Banco Nova Scotia, by the way, they have a lot of income in Mexican pesos, in the currency of Peru, in the currency of Colombia, and because that's where they do business, right? So, but most Canadian companies, they sell into the US, and you get paid in US dollars. What happens if the US dollar goes down? Bad. If the Canadian dollar goes up, or the US dollar goes down, bad, because your revenue comes down and your expenses are still there. If the US dollar goes up, good, right? Because your income now goes higher and your expense is still the same. So if you're a company and you have that risk, maybe you want protection against that risk. How can you buy protection against that risk? Well, you do a budget. Say, well, I'm going to assume that my Canadian dollar is worth, say, 70 cents US. I'm doing the reverse so that it matches my tree here, okay? So let's say the Canadian dollar is 70 cents US. But if the Canadian dollar goes to 90 cents US, so you go to the bank and say, well, if it goes to 90 cents, give me $1. You see? And then you can do your budget. So maybe it's not, maybe 90 is too much. We say, well, 80. It's at 70 cents. If it goes to 80, I'm still okay. But beyond 80, I'm in trouble, right? You go to the bank, and so if the Canadian dollar hits 80 cents, you give me $1. Or $10, or whatever the number is, right? And then, so yes, that's going to cost you. It's going to cost you some money. So of course, then I put that into my budget, but now I have insurance, right? The same type of insurance that you buy, when, say fire insurance or car insurance. Something bad happens, you get money, right? By the way, no one buys fire insurance for their home and then they hope the home burns to collect it, right? Yeah? No, this is important to know because many people think that when you, the buyer of these options, they actually want the option to make you money. Well, sometimes, speculators, yes, but oftentimes this is done by hedgers, which we'll see today. Usually you don't want your options to expire in the money. Usually this is protection against something bad, right? And I think my last example about this, and I think then we're completely done in terms of the significance of this, and then we can take a break, okay? Because we've learned so much. We've climbed such a tall mountain today with this example, okay? The last example I have is another expression of the power of math, which is perhaps a little bit unexpected. There was a very famous trade. It was a derivative trade. It was very simple, not as complicated as this. Sorry, it was much more complicated than this, but it was much easier to price. It was a swap. It was not it's a very famous swap, interest rate swap. It doesn't matter what it is. It's not relevant today. Interest rate swap between a US bank, Bankers Trust, and a customer. A customer was Procter & Gamble. You know Procter & Gamble? Have you heard? You use Tide detergent or something? Well, that's Procter & Gamble, okay? Very big multinational firm. They sell everything. And that was in the 80s, I think. Interest rates had a lot of volatility. We will actually see the 80s when we look at credit risk, because I have a business case from then, and you will see. Poof. So, this information is now very, very public. So Bankers Trust convinced Procter & Gamble to buy a certain derivative, a certain swap. Okay? And the sales department must have been really, really good, because they sold them a derivative, something like this, except that instead of, if it goes up, I give you $1, they had engineered everything so that I never give you $1. You give me your cents, but I never give you $1. Okay, it was a very famous swap. And there was, it went to court, there was a lawsuit, and because of that, some recordings, the bank had to present the recordings that they had with the client, and the recordings contained private conversations between the bank employees, how they were deceiving the client, and it was a big deal, and okay. And there was a settlement, okay? So Bankers Trust said, oh, don't worry, I'll give you, and then that's it, settlement. And it was accepted by Procter & Gamble, but one of the shareholders of Procter & Gamble, I don't know the identity, I guess this is public information, he got so upset. He said, no, a settlement? No, I don't want a settlement. But what can you do? Procter & Gamble settled, so you're a shareholder. So what he did, he took revenge against Bankers Trust, and basically accused Bankers Trust of doing things like this, and said, this is gambling, which is illegal in the state of New York. In Nevada would have been okay. Do you understand what I'm saying? Do you think that was considered to be funny by the bank? No. In fact, all of the banks, I mean, that's when derivatives were beginning to trade actively, right? Said, oh my God, all of this activity illegal? That was like a thunderclap. It was terrible, terrible. And one of the reasons, perhaps the main reason, that this was dismissed was precisely by explaining that there's no gambling here. There's a system of equations that tells you what the outcome is going to be, and that you can build a replicating portfolio. The mathematical proof we're going to see today was used as a defense that saved the derivatives market, because if this was gambling, if what I was doing with Zach was like what I did with Kevin, then there would be no derivatives market, because that would be gambling, and that's illegal in the state of New York. Okay, I need all of this to sink in. We're going to take a break, 10, 15 minutes, okay? Because now we climbed the mountain. Now I'm going to walk on the mountain. Let's see what other things we can see from there, all right? Good, okay.
Professor, do you mind if I ask a very quick question?
Yes, of course, go ahead. That's why we're here.
So I'm just wondering, have you been writing on the PowerPoint slide? Just
Not today.
Not showing up on the
No. When I write, you will see it. Today I didn't. I was using my hands a lot. I hope you saw my hands. Okay.
Beautiful. I couldn't see because of the camera, so just wanted to make sure. Thank you
Okay,
so much.
very good, very good. All right. My plan today is to go as far as I can, but I don't have a precise, the slides are there, you can download, you can see that I end with the fundamental theorem of asset pricing, but this is something that I care so much that you understand very well that I have no interest whatsoever in rushing. If I finish that theorem next week, big deal, I finish next week, but at least I need you to be ready for that. And like I said, I could have done this backwards. I could have started with the theorem, and then everything is just a consequence, and then guaranteed you will not understand anything. Guaranteed. I'll wait a few more minutes. Jonathan, your hand is up on Zoom. I suspect you already asked the question, or maybe not, I don't know.
Yes.
The part that I will be doing next Monday is largely based on what I'm doing today. So not being in person, being on Zoom, you will see it's fine, it works, it's gonna be okay. The Monday after, we'll do something a bit more complicated, okay? But it's okay, I've done this on Zoom many times, we're gonna be fine, you're gonna be fine. All right, so I think I'm going to continue. It looks like no one is coming in or out, so I think we're good to go. Great. All right, so I think I can turn the slide now. Go to a new one, okay? 1 hour with one slide. Good. All right. So, but everything that I'm going to be doing now, everything should be now completely obvious. Everything should be completely obvious. I think we've learned what everything that we saw here. Like what I'm gonna, like, why are you talking about this? I already know. That was the whole point. Okay. So probabilities should not fool us into thinking that the prices are given by probabilities, unless they are what we will define later on today, the risk neutral probabilities. That's the actual word, or the implied probabilities. Okay. The price is 1/3 because we can build a replicating portfolio. And note that it's because we can build a replicating portfolio and not because I can define the implied probability that prices the stock correctly. I haven't seen that theorem yet, so I cannot invoke it. Okay? The right reason, today, right now, before we see the theorem, the fundamental theorem of asset pricing, the real reason the price is 1/3 is because the replicating portfolio gives me that price. Great. Now, what happens if the interest rates are not zero? We mentioned that. And then there's two ways of doing that. One is, well, let's rewrite our system of equations. That's one. Or another one would be, well, my replicating portfolio is really this. The money I'm lending from Cheryl, right? Yes. The money I'm borrowing from Cheryl is really a bond, short position on a bond, right? Which is I get some money now and then I give it later to her. So let's just write it like that. A bond is a financial instrument that has a payoff of always one. A notional is one. Doesn't matter if the stock goes up, down, or stays the intermediate. It's always one. The price today is what changes. And that is what is related to interest rates, right? So that's why that replicating portfolio will always work independently of what the interest rates are. Interest rates do not change the replicating portfolio in this particular case. Interest rates will change the value of the replicating portfolio now. Because if interest rates are higher than 0, the bond is going to be worth less than 1, therefore the price is going to be more expensive. But the replicating portfolio is the same. That payoff will always be 1, 0. Yes? All right. Great. So then the option price, you just put in the value of the option there using the interest rate, instantaneous compounding, and that's it. So you have the option price as a function of the interest rate. Something interesting here is that I know we have an implied probability on the stock going up and down, but imagine that Zach and I were trading, and let's say that the price of the option really is 50 cents. So it really, then the interest rates cannot be 0. That's another way of resolving the fact that I'll be making money for free always. You see? That's another way. Because then, really, 50 cents. Then if you say 50 cents, then I go to Cheryl, say, Cheryl, I need to borrow some money. I say, yes, but the interest rates are not zero. That's what I would expect, right? Again, I'm assuming now that we're back into equilibrium, we're back into a situation where no one makes money. So if you insist in pay 50 cents, then for sure Cheryl will not lend me the money for free. Otherwise our theory will break down. And again, for a few weeks, we're assuming no one makes money for free. Can you calculate for me what the interest rates would be if we pay 50 cents? If you have, can you have pencil and paper? Can you do this? You have the equation there. And I think the answer is on the next page, but I still want, I need you to do something. What are interest rates if the price really is 50 cents? I'm assuming you can all do this. I mean, I'm asking you to solve an equation that you did in high school, maybe, or something. But I want you to see the significance of doing this. There's actually a very interesting result that you get. Anybody has an answer? What's the answer? What are interest rates? What is R if the option price is a half?
Log 2.
What?
Log 2.
Log 2. Okay, log 2. So R will be log 2, or about 70%. Okay? Let's remember that. Okay? Now, this is the definition of implied probabilities in our particular case. We already did it mentally earlier, but now I have the actual expression here, I have the actual definition. If I insist in pricing my option as the expected discounted payoff, I have to discount. With interest rates being different from zero, I cannot say that the dollar I get tomorrow is the same as the dollar I get today, right? If it's not the same for Cheryl, it's not the same for me. So then the cash flows, the payoffs that I have tomorrow or next year or in 5 years, they will need to be discounted to today with the discount curve. The same one that you're calculating on assignment number 1. So that is the expression that I have. That's the definition of the implied probability. And this measure that comes up is called the risk neutral measure. In mathematical circles, this is called a Q measure, and the P measure is the real world measure. So back to our example, when I say the probability the stock goes up is 50%, that will be P. And when we say, no, it's really 1/3 probability that it goes up, that's Q. Script P, script Q. Everybody calls them that way. P is the one that's given to you by opinions or something, and Q is the one which is built into prices. The implied probability is also called the risk neutral measure, and is typically called Q, script Q. Okay? All right. So this is, we already saw this. I know I can go fast because I think this is all very well understood. Okay? And we will say that the arbitrage-free price is equal to the expected discounted payoff. Under a measure, this is a mistake. That's Q. Okay, doesn't matter. I mean, I'm just giving you names, but the name that I used here is the name which is not usually used to denote the risk neutral measure. It's usually denoted by Q, not by P. Okay, what I said here is exactly right. It's just that I'm using the wrong terminology, usually called Q. And the result, for all of those who know this and care, is that the price is a martingale. A martingale is a stochastic process that the value of which at every point in time is the expectation of its future payoff or its future values. Okay? I'm not going to be doing I'm not going to do any martingales in this course. It means be the only course in mathematical finance that does not do martingales. I only mentioned the name here. I'm not going to do martingales here. Okay, I think you already understand everything that I want you to know. Great. So, what's happening here? There's something in the chat. Oh, yeah. Okay, great. So I'm going to close the chat. All right. So let me now look at this from the perspective of financial markets. Let me use this to understand financial markets a little bit better. This is the question I asked you to do, and the answer was log 2, as it was pointed out. Okay. But now let me ask a question. What would happen if my stock, the same stock as earlier, can take 3 values tomorrow? Not 2, but 3. We agree that 2 is very restrictive, right? Most stocks, they can take more than 2 future values. Let's say they can take 3. 2, a half, or stay the same. I introduce a third scenario for the stock. What would the price of my option be? Same thing, goes up to 2, I'll give you $1, goes down to 50 cents, I give you nothing, and it stays the same. Since I want it to be a call option, 1 minus 1 is 0, so I give you nothing. So I give you $1 only if it goes up, otherwise I give you nothing. What's the option of that? What's the price of that option?
It depends on like the probability of the underlying events, basically.
Never say probability anymore. Okay? Never say probability anymore. We're not going to use that word anymore. Right? And this is, I mean, you can say, well, the implied probability, but not the implied probability is now clear because I have 3 events. Right? You can say, well, let me go back, and I know I haven't proved it yet, but what's the probability, the implied probability of the stock going up and down, just looking at the stock? I don't have enough information because I have 3 events, and yeah, I have P, Q, R, they add up to 1, and I have 2 equations, 3 unknowns, right? You cannot solve it. You cannot solve it. So what do we do? All right, so this is a situation, there's a term, there's a name for this situation. It's an incomplete market, meaning we have infinitely many answers. You will see, all of this is going to be covered by our theorem, okay? It's very similar as when you have in linear algebra more unknowns than equations, right? You saw that. Typically you have infinitely many. You can parameterize them. It's going to be exactly the same thing here, exactly the same thing. We're going to have a price manifold that we'll have to select taking other considerations, but the price is not unique. Or there's another alternative to that, which is we can introduce an additional trading day between now and maturity. And once we do that, then it gets real fun. Because, let me just see, because our theory will become time dependent. I'm going to stay with the time independent theory. It's called a one period finance, one period, single period. Okay, I'm not going to introduce the multiple trading dates yet. I'll do it later, I think today. But so I want to develop the fundamental theorem of asset pricing in the case of a single period finance, so only one period, no trading halfway through, which will resolve the incomplete market. We want to deal with incomplete markets also in the context of one period finance. And what we're going to do is we're going to introduce some terminology, which is same thing we saw earlier, but now everything written in matrix form. And I start with the payoff matrix. The payoff matrix is the one that has the values of my financial instruments in the future expressed as columns. So each row is an instrument. Each column is an instrument. Each column is an instrument. And each row is a scenario, is an event. Here we only have two events. The stock goes up, the stock goes down. Okay? So the matrix has, the way we read the matrix is instrument number one is the bond. If the stock goes up, it's worth $1. If the stock goes down, it's worth $1. The bond is always $1. Then the next column is the stock. If the stock goes up to $2, it's $2. If it goes down to 50 cents, it's 50 cents. That's it. All the information about the market future values is in the payoff matrix. And we write it like this. Of course, you can write it in transpose form too, and then everything will change. Fine, you know that. This is the way I like to write them. Okay, that's the way it's just the way I do it. Most people do it like this, but there could be texts that do it differently, and that's okay. Then my replicating portfolio is a vector. It's a vector, okay, XY. X representing the number of bonds, Y represents the number of stocks, or you can use your favorite nomenclature for the vector. You can say X1, X2, or V1, V2, or UV, up to you, whatever you like, all right? And the characteristic of my replicating portfolio is that the multiplication of the matrix by that vector has to equal the payoff. And now you have to be careful. You have to be consistent, not careful. You have to be consistent with yourself. Given my choice of columns and rows, the multiplication of the matrix times the replicating portfolio has to be on the left. Okay? Just make sure that you have each instrument multiplied by its future price, not someone else's future price. That's what will happen if you flip the D and the XY vector, right? So we already did this in your heads. This is the reflection that the replicating strategy is the solution to a system of equations. And now here it is explicitly for you, with the advantage that if we organize our data like this, then I can deal with enormously large universes of securities and scenarios. Right? This is an exercise in data organization. That's all it is. And if I introduce a cost vector, which I write it here in row form, the cost vector is how much a bond costs, how much a stock costs. So the stock is $1, as in my example, and now I'm saying the bond is 90 cents. So Cheryl is now charging me 10% interest rate, more or less. Right? Fine, all good. And the price of my option will be the price of the replicating strategy. The replicating strategy will have a price which is the product of my cost vector times my replicating portfolio vector. And I wrote it because I was lazy, perhaps, that X would have an arrow on top, meaning it has really, I'm not referring to the first component of the vector X, right? It's the vector X, two components, X and Y. So maybe X with an arrow, that would be more accurate. Or if you like, you can unwind, because X is the inverse times that. You can also write it like that. Right? So the price is what is it? Now this is interesting. Let's read this off. I have the payoff vector times the inverse of the payoff matrix. So that's the discounted payoff, right? I'm taking the payoff later, and then I'm applying the inverse of the payoff matrix. That's the way to discount those values to today's dollars. And then I multiply by the cost vector, which is what will give me the expected discounted payoff. Expected discounted payoff. So it's the same thing we said earlier, it's just that now it's written in matricial form and in a way that you can program this in a computer very easily if you have all the data in front of you. And you already know the problems you're going to run into, which are largely going to come from matrices D, which are not square. As long as your matrix D is squared, you're going to be fine. Square and non-singular, you shouldn't have zero eigenvalues. It should be invertible. As long as it's invertible, you can do this. You can put this into a computer, program this in Python, and in a millisecond you have an answer. How many stocks can you deal with? How many securities can you deal with here? Okay, let me have a poll. Who has done programming, probably in Python, with matrices? Okay, how big a matrix did you go to when you were doing this? How big? Let's see who's the winner.
It was like 26,000 in one of the dimensions.
26,000 by 26,000.
No, it was 5 closed squared by 5 closed.
So give me an idea of the dimension of number of rows or columns.
The number of columns was 5 closed, the number of rows was 5 closed squared.
You see, I couldn't hear you. 5 what?
5 closed squared is the number of columns.
5 something squared.
I don't know how much 5 closed squared is.
About
Okay.
10 to the 7. About
Okay,
10 to the
okay. And your name, by the way?
Jonah.
Jen. Okay.
7. It's too small.
It's too small. Yeah, yeah. So who's done bigger than that? What have you done?
I did 10 to the 7 to 10 to the 7.
10 to the 7 times 10 to the 7. Okay, so
It
that's
depends on your hardware. So like in the compute calendar cluster, that's the limit.
Okay.
You don't have any like up here.
so 10 to the 7. Okay, 10 to the 7 is reasonable, right? Reasonably big. I mean, right? Reasonably big. By the way, let's talk about sizes of matrices now, a little bit. Okay, so really no one has done very big numbers in matrices here. Your Python experience is limited to small matrices. Yeah.
You are bounded by your hardware.
Okay. All right. Okay. Okay, yeah, I'm not going to get distracted. I feel tempted to getting distracted by this. I'm not going to get distracted. I'm not going to get distracted. But let's stay here. How many securities do you think we have out there? How many stocks in North America? Okay, how many bonds in the database that you were using for your assignment? How many bonds? 40, right? So that means that, I know that we're not doing options on bonds, something different. It will all be the same in the end, okay? It will all be the same in the end. But if you have 40 securities, your payoff matrix is like 40 by 40, right? Stocks, how many stocks are there? Let's say you're doing Canadian stocks, how many stocks in Canada? A few hundred. If you're doing the US, how many stocks in the US? 10,000, 20,000, right? So you'll be dealing with matrices which are in the tens of thousands by tens of thousands. So still small compared to what you were doing, right? So for many of these applications, you don't need very large matrices. These matrices will be tiny compared to what a computer scientist will call a challenging matrix. These matrices are not challenging. Not for your database, not for your calculations. Unless you're trying to do something weird, like for example, eigenvalues and eigenvectors. Those are expensive. But now I get sidetracked. As you can see, the worst we have to do here is what is take an inverse. Okay. When will your computer start to sweat? If you ask for an inverse, is really solving a system of equations, right? So at what dimension will your computer start to sweat? Say, oh, that's too hard, I can't do that, come back tomorrow. At thousands, it's going to start to sweat a little bit, all right? But it's doable. It's not a problem. You don't need to be a genius. You don't need to be Larry Page. Okay. By the way, you know the Larry Page theorem? No, I should tell you. It's a beautiful theorem. That's how I start my course when I teach computational methods. That's my favorite theorem. But we'll do that some other time. When you have a matrix which is like a billion by a billion. That's a challenging matrix. Yeah. 10 to the 9 by 10 to the 9. That is good. Challenging. All right, let's continue. Okay, there we go. So is this clear? I haven't done anything. I just wrote it in matrix form. But it's to be expected. We already, in fact, the very first answer I got to my question was, your name?
Daniel.
Daniel, right? Was you were solving a system of equations. So it's just natural. It's natural that we do it like this, right? So let me pose a question. Let me go back. Let's see if you can memorize this. It's in the notes. I don't want to be going back and forth. It's easier to express and for you to remember than to go back and forth. Remember that scenario when I told you that my stock was $1 today and could go to $2.50 or stay constant at $1? Remember that? Okay. What if I told you that the option that we traded earlier with Zach continues to be at 33 cents? What if I told you that the price of that option is 33 cents? And then I ask you, sorry,
I think you should get a complete solution then.
no, but then I ask you, what would be the price of the option that would give me $1 when the stock, that will give me 50 cents. No. Yes, that will give me 50 cents when the stock goes down to 50 cents. Understand what I'm saying? I'm changing the game. Who wants to play that game with me now? I need a different counterparty. Daniel. Okay, so we're playing the game, right? I'm still trading with Zach at 33 cents, the same option. I didn't change. The market changed, but we continue to trade at 50, and okay? And Shell still gives me interest-free loans, and right? And now we have, wait a minute, the stock can actually stay constant. It's a new scenario. We're changing the problem. I'm adding a new row to my matrix, right? A row in the middle, which is, so that will be a 1 for the bond, but in here I put a 1. Sorry, what a messy thing. 1, I put a 1 right there. Yeah? And I put, well, it has to be a 1, it's a bond. The bond is always 1, right? I put a 1 right there. But I tell you that we're still trading the option at 50 cents. What happens when I say that? What happens is that this matrix has suddenly a new column, which is 1, 0, 0. That column is added right there. You see? Now have a 3 by 3 matrix. So I'm telling you what? We're going to play a game which is I pay you nothing if it goes up, nothing if it goes up, and half if it goes down. That's the game we're playing. Big deal. Same answer. Well, expressed like that. The same, the inverse times a new vector, 0, 0, a half, times the cost vector. You see? This is a way to resolve what is called a incomplete market situation. okay, when I have suddenly more rows than columns. That's an incomplete market. I complete it with that particular, and there's something interesting that I want you to notice here, which is in financial markets, a stock, a bond are considered to be financial instruments, and then a derivative is a derivative on a financial instrument, right? There's a hierarchy in finance. An option is called an underlying asset. That's the stock in our case, okay? But from this perspective, we don't care. We don't care. An option, a stock, a bond, we don't care because everything is defined by their payoff, how much money they actually give you at a point in time in the future. See? We've deprived these financial instruments of their financial meaning. That's why it becomes so simple. For us, they're just payments into the future. That's it. Don't care if they're stock, bond, or options.
Was the cost vector given, or was it?
No, the cost vector will be here. Good point. I forgot to put that. I said we're still trading at a third, right? That's the cost vector. Yes, right. You see, this is magic. Because now you can have as big a system, a financial system as you want, with stocks, bonds, derivatives, whatever. Just instruments that when something happens, they are worth something. That's the database you're going to build. And you can build it yourself. And you can make it as big as you want. Thousands is okay, right? No problem.
So how do people actually do that? I mean, how do you know the new equation you introduced will not violate consistency of the old?
Oh, well, there's a theorem. The theorem will tell us. Okay, and by the way, if there is a condition that violates this consistency, that means that there's an arbitrage opportunity. And if there's an arbitrage opportunity, what do you do? Immediately, quickly, because it's not going to last, right? So you're the first one who realizes, wait a minute, there is a negative eigenvalue here. We'll see, okay? Then find it and start trading. Like someone is paying too much for something, right? So sell it to them. This is real. I mean, I'm giving you the matrix version of what is real. And this is how these markets developed in the 80s with these smart people from Princeton and Harvard and MIT. Yeah? Do you feel yourselves you could do this, right? Database of prices and scenarios, yeah, you can do that. And then you can price anything. Right? Okay, I think we're ready for the theory. So all of this can be put into a theory. Now, I'm about to tell you the one-period pricing theory. Now, before I do that, let me tell you there's a multi-period pricing theory, which I'm not going to do. I'm going to do the one period, and then I'm going immediately to continuous time trading. I'm not going to stop at a few points. Why? Because several reasons. First, the only reason I'm going to give you this theory, this theorem, the only reason is I think from a pedagogical perspective, it's interesting to see how a theorem can be so reassuring in practice to know what you're actually looking for every single time you're trading. Okay, it's pedagogical reasons. It's, believe me, no one proves theorems in banks. Well, hardly anybody proves theorems in banks. Okay, I'm not going to say that theorems are even important in banks, but as we are learning this, why not devote one day, why not today, to a theorem that, as you can see, has so much relevance in this mountain we just climbed today called the pricing theory mountain. Why not? Okay? I don't want to overemphasize the relevance of that. That's why I'm not going to do the theorem for multi-period pricing. There is another one, it's very complicated, and I'm not going to do that because I think my mission will be accomplished if you see the single period theorem. Okay? But for multi-period, imagine I ask you to price this option for me. This is a stock that I have here, You see, I give you just examples of what it can move to. 2 days, but so 2 trading days and then a maturity date, but I could do this for days and days, and then it could be every day, these are the prices, and then after a year I'll have, how many points after a year?
If you take them daily, then 365. Well, actually depends when the market's open. But
Exactly, depends on how many days, but if there are not too many holidays, then 2 to the power 300 or something, right? That'll be the number of nodes you'll have at the end of that. 2 to the power 300 is how much? Two to the power 300.
it's like ballpark, like 10 to the 100, like a bit less.
10 to the 30, I think, no? The logarithm of 2 is 0.3, so logarithm base 10 is 0.3, so that's about 10 to the 30, that would be my guess, right? That's a lot. It's bigger than your matrix, huh? So maybe it's not a good idea to... Wait a minute. How do we resolve that?
Prune the tree.
Okay, so you what do you do?
You prune the tree.
You prune the tree. Okay, so I can see that you come from machine learning, right? That's what people do in machine learning. No, in finance we don't prune trees. We don't do that. What we do is we make the trees recombining, which means when the stock goes up and down and down and up, they go to the same point. Just that. And I'm not sure if you're following this. We're going to see this more systematically. But what happens if the stock goes up and down and down and up? If they come to the same point, then how many nodes do I have after a year? 300 times 300 divided by 2. So very, very small. See the difference? Huge difference. The difference between a combining and a recombining tree. By the way, I'm going on a tangent, I know, but it's an important tangent. I'm coming back, okay? By the way, a tree which is like this is a non-Markovian tree. And a recombining tree is a Markovian tree. Do you know what that means? Markovian processes. What is a Markovian process?
Memoryless.
Yeah, a Markovian process has no memory, okay? So you're where you are, and yeah, you came here from the past, okay? When you ride the subway, you're in a Markovian tree. You can go Queen's Park here, or you can go all the way around, and when you get here, right? But if you remember where you were, then it makes a big difference how you got here. So that's a non-Markovian tree. Non-Markovian trees grow exponentially fast. You don't want them. You don't want them. You don't want to have to prune them. No. You want Markovian trees where you're going up and down, down and up, you get to the same place. Okay? Okay. Now that footnote you can now bury. It'll be more relevant. Like it's done in more detail in the book. If you're doing the book, you will see I have some questions about that. That's if you're doing the book. But let's say that I give you this option, and I give you, this stock process, and I ask you, what's the price of the option to buy the stock for $75 at maturity? Let's convince ourselves that we've really learned a lot with this single period finance before all I talk about is single period finance, okay? So what am I saying? I'm saying that the stock is here, it's $80 now, and then it's going to mature in 2 days, not in 1 day, but in 2 days or 2 years, and you can buy it for $75. I think I'm using $75, I'm pretty sure. You can buy it for $75. That means that if the stock ends up there, you don't buy it. Ends up there, you don't buy it. Ends up here, the option will give you $5. And if you're here, the option will give you $105. That's the payoff, right? So the payoffs would be 105,500. That's my payoff. But that's at maturity, and that's after 2 steps. How do you find the price of the option now? How can we do this? Yeah. Yeah, exactly. So what I do is, this is why the single period finance is so powerful. What I do is I want to change colors, maybe green. Okay, so what I do is I do this one first, right? This you can do. This is single period. You have the stock and you have the option. The option is 105 and 5. So you can find the price now. I have it in the next slide. I have the answers, I think. Okay? I'm not interested in the answer. I'm interested in the algorithm, the process. Everybody sees that? Just close your eyes. No, keep one eye open, close your other eyes, and just focus on that branch, right? Then price the option, which is conditional on the stock being 120. We know how to do that. And we can do that in how many ways? Replicating portfolios, expected discounted payoffs, implied probabilities, matrices. Yeah? We have many ways of calculating that price. Let's do that one here. Same thing, another single period. This one is particularly easy. What's the option value, assuming the stock is 60? You don't need matrices for that. 0 is an option that if the stock goes to $72, it gives you nothing, and if it goes to 36, it gives you nothing. How much is that worth? What's the replicating portfolio? Who cares? Right? All right. And now, once you have these two, I'm going to change colors again. Then you go to today. So you have this single period expression. And I have an option, okay, that if the stock goes up to 120, it's going to give me some number I calculated previously. And if it goes down, I get nothing. So we know how to do that one too. Right? So I can get the answer. That's how you do it. That's why one period finance is so powerful, because then I can do multi-period. And that's when this goes, I don't do multi-period. That's all the multi-period I'm going to do. No, that's not true. No, that's not true. I'm going to do a very, very interesting multi-period pricing exercise at some point. It's actually very interesting because when I do that, I will introduce, have you heard of the Air Canada flight passes? The flight pass, Air Canada flight pass, you know where they are? No? Okay, well, I'll tell you one day, but I'll tell you, I'm flying today, so I am very much I have my boarding pass in my pocket. These are the things that I think about today. So Air Canada has flight passes. If you fly frequently, you can buy a flight pass, which is essentially a guaranteed price, right? It's an option. You don't have the commitment to fly in sometimes. I mean, I used to buy them when they were a good deal. Now they're a ripoff. I don't want to do them. But I bought them for a year or two. And I used to go to New York very often, like once or twice a month. And so you buy, I don't know how many, 6, 10, I don't remember. Okay. And then when I go to New York, I check the prices. If they're expensive, I use a flight pass. If they are cheap, no, I pay and I go. Right? So I have the option, not the obligation, to fly to New York at a given price. So that will be an example. I'm going to price a flight pass for you, which is very, very interesting. Very, very interesting to price. Not only they are useful for flight passes with Air Canada, they are useful in the energy markets. They are used every day. Okay, and we'll see that. That is the one thing I will do in multi-period finance. And the reason I will do it is because it's not a straight iteration of single period finance. That is not a straight. You need to think. There's something very interesting that we'll have to learn there. This is the one exotic derivative I will do because we're surrounded by those. There's going to be more and more and more of those. Not just the flight pass, lots of others. But except for those, this is so simple that if I do a good single period finance, you can fill in the blanks for the multi-period finance, right? Yeah? You see that? Did I convince you this is easy? Good, it is easy. There's no mystery. Where it gets complicated is if you take infinitely many steps. When you take this to the limit, when the time increment goes to 0 and the price difference, then you have to be, that's very tricky. Very, very tricky. That I will do in great detail again. But that's a different mountain. That's the mountain of continuous time finance. We'll climb that mountain maybe in 2 weeks. Okay? But for now, you see, if I can do multi-period finance if I'm good at single period finance. You see that? Good. So let's do single period finance and we'll skip this. No point in doing this. No point. Great. So I already did this. I don't have to do that again. All right. So this is what I want to do. So my apologies for the typical mathematician slide, full of symbols and letters and words and stuff like that. Okay. I like to teach communications. In fact, at MMF, I teach communications, and having a slide like this is against the rules. You cannot do that. But sometimes I have to break the rules. All right. So what am I doing here? This is what I'm doing. I'm not scaring you off. At least I'm not trying to scare you off. I know that this is scary when you look at this. What is this? No. Well, first of all, it should be clear that we're getting ready to do a theorem, right? This is what happens when you're getting ready to do a theorem. You start to see all of this. You're surrounded by notation and variables. It's, oh my God, when is the theorem coming? And you're like afraid, right, that the theorem is going to step right in front of you and say something to you. Okay, so, well, don't worry. It's going to be, we've seen all of this already many, many times. I'm just organizing all the information and all the notation and everything that we have done. I'm just organizing everything we already know so that my theorem becomes very, very painless. Okay? I'm organizing not data, but the information we have in such a way that the theorem is very painless. By the way, for those of you who know, the theorem, which is the fundamental theorem of asset pricing, is after I organize my information, is going to be a version of the risk representation theorem. That's if you know functional analysis. The risk representation theorem, you know that? Risk representation theorem? Yes? Okay. Okay. If you don't know the risk representation theorem, since I will do the finite dimensional version of it, the risk representation theorem says that it's something that you show in linear algebra. If you have a linear map between a Euclidean space and the real line, a linear map, it's a multiplication by a vector. Right? Linear maps are matrices. If I go from space n to space 1, it's a multiplication by a matrix which is n1. That's a vector. Yes? Yes. Well, that's what the theorem is. I say, what kind of a theorem is this? You've known this forever. Well,
That's for L2.
what?
Well, you said it's for L2, right? But you can have that.
If it's for L2, yes. It's for, the thing is that when you are in finite dimensions, everything is in L2, right? So some of you may be thinking, oh, of course you knew that. Every linear map is given by multiplication by a matrix, right? You saw that. Well, that's what will happen when I organize my information well. If I organize my information well, the fundamental theorem of asset pricing is going to boil down to the statement that the linear map is multiplication by a vector. Right? So that's why it's worth going through this. But there's nothing new here. There's nothing new here. Okay? I'm going to look at first of all, there is events that could happen. That's how we have the payoff matrix. Therefore, there's going to be a probability space. The probability space we have here is the P1, is the one which is wrong, so to speak. Of course, it has to be this, because if I say we start with the right one, I'm in trouble already. I need to define what the right one is. I don't want to define the right one. The right one will be a consequence of my theorem, right? So I have to start with the wrong one. You see, the first line is basically saying what I did at the beginning of class. There's a 50% chance the stock is going to go up and a 50% chance the stock is going to go down. What comes after changes. Okay, in the game I play with Zach. That's what I'm saying there. My 50% up, 50% down is my first line. I'm assuming that there is a probability space that tells me where securities could go and with what prices. That's it. Okay? It's just that I have to write it like this. I have to be a mathematician for, I don't know, half an hour. I guarantee I'll end in half an hour. I have a plane to catch. So I will end, okay? Don't worry. Good. So a security for us is not a, what is a security in the real world? A security is a contract. A bond is a promise to pay, which has some specified conditions. What is what's a stock? It's a participation in a company with a shareholders agreement this thick, right? Okay, so securities are contracts. They are legal entities. Today, for this theorem, no, a security is something very, very simple. I only care about how much it's worth now and how much it's going to be worth later. I cannot simplify it more. Okay, anybody is in finance here? Like finance? You'll be insulted by this if you were. The whole point of finance is to look into all of the nuances of securities and their rights and shareholder rights and voting rights and proxy voting rights and all of that stuff. That's what finance, that's what makes things happen. I'm ignoring all of that. A stock is a price that you look up on your iPhone. That's what I'm saying. Okay? Because that's what I need for what I'm going to do. You're with me, yeah? Okay, good. All right. So each security will have a cost. I call it Q. I'm assuming there's n of them, so I'm assuming there's a finite number. But if you like infinite numbers, n could be infinite as long as everything is L2. Okay? For those of you who know what that means. The payoff is a random variable because I'm assuming finite events is just a vector, a column vector, as we saw earlier. You like L2, you can make it a random variable with infinitely many values. I don't care. It's the same thing. Okay? So here you have a choice. You can. I'm writing in abstract terms everything we saw today, or if you want to go a step further, I'm generalizing everything we saw today into a space with infinitely many securities and infinitely many possible events. The theory is the same. The expected payoff is the expectation of my payoff. Not very hard, is it? The expected payoff is the expectation of my payoff. The expectation, according to the wrong measure, 50-50. But the payoff is that column that is given to me. Yes? If this is just a definition, this is going to be nowhere near the price. Well, actually, yes, the price will be this, but conveniently changed. We're going to find the exact way to change the probability so that the expected payoff in a different space is correct. And for those of you who know this or care, let me give you a spoiler. Spoiler. Big spoiler. We're going to modify our probability space with a random Nicotin derivative of the Q measure. That's the spoiler. Watch it when it happens, okay? Those of you who don't know what the random Nicotin derivative is, it's okay. It's okay. All right. I hope you're all with me. I hope I didn't lose anybody in this sea of symbols. The portfolio is a vector. This is not new. We already saw that, except that I'm writing this as a vector notation for the first time. Okay? A portfolio is a vector, and a payoff matrix is a matrix. Okay, what else? If the component is positive, I'm long. If it's negative, I'm short. Yeah, of course. A portfolio has a payoff, which is the product of the vector times the payoff matrix in this sequence, I think. And the result is a random variable. A random variable for us, because we're in finite dimensions, is just a vector. Okay, I'm beginning to suspect this is the other way around. Multiplication is on. Can you help me? I cannot think when I'm in the podium, but something tells me that this multiplication is on the other side. Is this right multiplication or left multiplication? I could make this a question, claiming that I know the answer, and it's just for you to think, but it's not true. I actually don't know the answer right now. I suspect I made a mistake, but I don't know.
Yeah.
Hmm?
That's not, it's a dot product.
What?
I think it's the dot product.
Is the dot product, is it? Oh, the dot product, yeah, the dot product of, yes, of course, yes, you're right, yes. Yeah, it's the dot product, therefore would be the multiplication with the matrix on the left. Yes, it's fine, you're right. Thank you, yes, it's the dot product. Yeah, so it is correct, oof, good. One less change to make. It is correct, it's the dot product, thank you. Did everybody understand the question and the answer? Yes, okay, it's the dot product, there you go, all right. So that's the payoff of my portfolio, and then a market is said to be complete if the span of all possible payoffs gives me all of the possible payoffs that can exist. And I denote that here L2 of mu, because it's the only way I know how to write that. So that would be my entire space of all payoffs. In other words, a payoff is complete if the basic securities that make my market give me all the payoffs that can possibly exist. When I introduced that stock that had 3 payoffs earlier, and I said that market was incomplete, why did I say that? I said that because with the payoff of that stock and the bond, which is the only thing we had, we could not replicate, meaning the span of that was never equal to the option, which is 100. See, it's consistent with that. But then once I said, no, let me take that option and put it into my universe and I'll give it a price of 1/3, then suddenly my market is complete. Because with those 3 payoffs, 111, 100, and my stock, which is 2, 1.5, with that, I generate the entire 3-dimensional Euclidean space. Yes?
What is the mu?
Mu is my probability. So this is my L2 mu here. Okay? Are you fine with the jargon that I'm introducing here? Yeah?
Professor?
Yes.
Can I ask a question?
Yes, of course.
Okay, so the question's about the portfolio vector. I'm just wondering, can these vectors be combined if they have different dimensions? Like in the way that we, the reason I'm asking is because we can't combine matrices of different dimensions, right? But I'm wondering maybe with, I don't know.
No. So let me say something, okay? Let me say something. There's 2 dimensions that I'm playing with here. One is a dimension given to me by the number of securities, so I don't think that's the one you're talking about. The other one is the dimension which is given to me by the payoffs of each security, and I think that's the dimension that you're talking about.
That's correct.
Yes.
Yeah, so like some securities will pay off, based on their price.
I know.
Some will pay off based on dividend.
No. You just said something very interesting. Let me pick on that. Okay, you said some will pay depending on the price, some will pay depending on the dividend. Not according to this framework. According to this framework, the dividend will be part of the payoff. Everything is in the payoff. Again, I'm stripping finance of everything it has, except for the price now and the price later. That's it. Okay?
That makes sense.
Yeah. It actually does make sense, but it's an oversimplification. You should know that. And I said it, right? I said, I am stripping stocks of everything meaningful to them and assuming that a stock is nothing but a price now and a price later, and that's it. That's number 1. Number 2, in case you're thinking that a certain stock is not going to be affected by some other stock doing something different, that's not the way I'm setting up my data here, okay? My scenarios include stock A going up and stock B going down, and there will be different scenarios. So I'm considering all of the possible scenarios combined that could happen in my market. Okay, so for example, I'll give you an example. And again, I don't know if this was part of your question, but it's something that we should all be aware of this. Let's say that I have one bond, two stocks. Yes? And the stock, they're both $1 today, and one can be $1 tomorrow or 50 cents, and the other one can be $1 tomorrow or 50 cents. What's my probability space? 4 events that can happen tomorrow. Up, up, down, down, up, down, down, up. Right? And then under each of those, each of the stock has a price. See? Okay? So when I say here a probability space and the payoffs, that's exactly what I mean. It's everything that could possibly happen that has to be in my space. Understand, right? So it's a massive matrix that we have here. You start adding stocks, massive. You start adding events that the stocks could do, massive, right? The market could easily become incomplete if I have a lot of scenarios for certain stocks and not enough other derivative prices or something like that. We already saw that, right? For example, it's very easy to check that as long as each stock has two values, I can add as many as I want, and my market will always be complete, right? But if I add one stock that have three values, well, I better include some derivative somewhere and whose price I know, otherwise my market will be incomplete. It doesn't matter if the market is incomplete, my theorem will still hold, just will not be very useful. Okay? So is this slide now like even easy? There's nothing new here, there's no new information. There's no new information. I'm just organizing everything we discussed today in a way that gets me ready so that my theorem is one page. Yes?
Just to confirm, so L2 is functions.
Yes, the payoffs, they're payoff functions, yes.
Mu is mean of the random variable.
No, mu is the measure. Mu denotes the measure, is the measure. Okay, so mu is the measure. Mu is, mu of a set is the probability that this happens. I'm using that notation. So this will be the equivalent of what I called the P measure earlier in my presentation. No, it's not the expectation. It's the measure. I was very ambitious when I wrote this because I wanted to write it so that if you don't know infinite dimensional algebra, functional analysis, then you understand everything that I'm doing. But then if you do know infinite dimensional linear algebra, functional analysis, then you see, oh my God, this is the Radon-Nikodym theory, this is the Hahn-Banach theorem. You can see how all of this goes into infinite dimensions very easily, very quickly. So that's why I'm using, it's just if I write a lecture which is in English and in French because I want to get the best of Balzac and the best of Shakespeare, right? That's what I'm trying to do. And it's a Frankenstein, but in my experience, this actually works so that everybody gets to understand as much as possible. Yes, you had a question. Speak up. I have to get closer to you. You don't speak.
She asked this L has any meaning by itself, like without the square.
No. So L2, this is a very good question, by the way. I suspect you don't know what L2 is, right? Okay, so this is a very good question, especially for those of you who do not know what L2 is, although you have seen L2. The reason is everybody has seen L2 because at some point when you were studying calculus, someone introduced to you, probably to harm you, the space of functions with the characteristic that the integral of the function square is less than infinity. You have seen these functions, right? Yeah, so this is L2. And the thing is that this, I don't know if they introduce this to you to harm you. Sometimes they do that. Other times we introduce this because these spaces of functions are the only ones in which certain things make sense. For example, I told you about music the other day, right? And I said that every sound can be decomposed into its fundamental frequencies. Only they are here. If they have infinite energy, then the answer is no, they cannot be, right? So these are the spaces which are so nice that most of the things that we see happening, they actually happen, right? Things which, things with infinite energy, things, they're not here. So when we describe things which are normal, whatever normal means, then these are the spaces of functions when things matter. So this applies to music, this applies to quantum mechanics, this applies to these securities too. Okay? If the payoff is not square integrable, then that payoff is not going to be treated by this theorem. Of course, that implies that I have infinitely many securities, infinitely many events, blah, 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 infinite dimensions. And for most of you, I suggested just restrict ourselves to the finite dimension, but I put that there so someone like you would ask me the question, and then I will give you the answer. You see? And now, after saying that, I can say, if you don't know what that means, let's just replace that by R to some power. That's it. Euclidean space. Okay? Matrices and vectors. We're back to matrices and vectors. I say once more, I'm not doing anything here that we haven't already done in dimension 2 by 2. I'm not. It's the same. Okay? But this is what will allow me to deal with very large sets of securities and very large sets of payoffs. How large? If you respect what's here, as large as you want. Infinite is okay too. That's why this is so powerful. Okay? All right. Good. Good. So I can go to the next slide. It's going to look easier by comparison. So the cost of a portfolio is the cost vector times the portfolio vector, dot product. That's not very hard, is it? This is what you learn. You're in kindergarten when you learn this, right? An apple is 5 cents, and a pear is 10 cents. How much is a pear? And an apple is 15 cents, right? Okay, so that's fine. How about the return? The return is the ratio between the payoff and the cost. That you don't see in kindergarten. You see that a little bit later, grade 5 maybe, right? 10%. When is the first time you see percentages? When did you see percentages for the first time? I'm curious. I don't know.
Yeah, in grade 5, grade 6.
Grade 5, 6, yeah? Sounds about right? Yeah, well, it's the same thing, except this is in a Hilbert space, but it's the same thing. Oh, by the way, L2 is a Hilbert space. That's the word that it has. That's it. All right, let me continue. So we're good here, right? Okay, so what is an arbitrage opportunity? As I mentioned, arbitrage opportunity is making money with nothing. So mathematically, that's expressed like that. An arbitrage opportunity is a portfolio that has a non-positive cost and a non-negative payoff. Doesn't cost you anything, and it's only going to give you money. But it has to give you some money for sure with a non-zero probability. So there's a version which is called weak arbitrage, which removes that. Okay, now there's many different definitions of arbitrage. I'm not interested in all of them. This is the one I need, and that's the one I'm going to use. Okay? Making money for nothing, and we express it like that, a portfolio with a non-positive cost and a non-negative payoff. right? That's an arbitrage opportunity. It's the definition. It's a vector. If there's a vector with this characteristic, then that's an arbitrage opportunity. The efficient market hypothesis is a hypothesis that says that there's no arbitrage, everybody works for free, and there are no transaction costs. Everybody works for free. Okay? And that is what we're going to assume today and maybe tomorrow for a little while. Because that's when things make perfect sense, right? But then we'll remove that so we can make money as much as possible later. Okay? Okay. Everything good? Yeah, we're climbing the mountain of abstraction, but we've already dealt with all of these concepts. This is my theorem. And I call it the risk representation theorem because that's really what it is. That's really what it is. Okay? So if I have linear functionals of the payoffs, what does that mean? A payoff is a matrix, right? They're vectors. So if I have what's a linear function of the payoffs? A payoff is a vector. So if I have an operation, a linear operation of vectors, actually price is the one that I care about, is the actual payoff itself. So the linear function I'm interested in is the identity. But this theorem is so general that I can apply this to some other thing. So that's the one, is the one that I care about the price. Then there's a random variable. This is the big deal. This is the big deal. There is a random variable. What's a random variable, by the way? A random variable is something that has values in every event that could happen. There's a random variable, mysterious random variable, so mysterious I call it pi. Pi because price starts with a P, so I have to sometimes take a Greek letter and pi. Why not? You know why this circumference of the circle is called pi? Anybody from Greece? Anybody speaks Greek here? No? Perimeter is perimetro in Greek. I don't know Greek, but it starts with the letter pi. I know that. Yeah, that's the P in Greek. That's what it's. So portfolio is also. So I write it pi. Yes, and price is. So I write it pi. I like pi. So I rate it pi. It's a random variable, but I rate it pi. Big deal. And look what this does. This is the price. The price of my portfolio, this is my theorem. The price of the portfolio is the expectation with the wrong measure. Remember the 50-50 is the expectation with the wrong measure of the payoff of my portfolio. This looks wrong. It's telling me that the price is the expectation of the portfolio payoff. The portfolio payoff looks wrong. Why is it not wrong? Because of pi. Pi is changing. Every event gives it a different weight. What pi is, it changes the weight of every event so that it has the right probability. Okay, so let me go back to the example we started with today. I said 50-50, right? And then we saw it's not 50-50, it's a third, 2/3, right? What's pi? What's this pi? Someone tell me this pi. It's a vector, 2 values. What is it?
2/3. 2/3.
The first one is 2/3. Yeah. And the second one?
What was it again? It was 1/2.
Is it 0?
Is what? No, not 0. No. 4/3. Yes, that's the pi. Why? Because I said 50-50, right? I said 50-50. Wait a minute. You're tricking me, right? 50-50. So Zach says 50-50. Excuse me. 50-50 times 2/3 is 1/3. 50-50 times 4/3 is 2/3. Now you don't pay 50 cents. You pay? One third, or you're not going to get rich. One third, right? See, what this SPY does is it takes the bad information given to me by your financial advisor and gives me the right information that prices all the securities in the market, right? And it does that by going every event and say, no, that's the wrong probability. This is the right one. Multiply by this number and you get the right one. That's how this theorem tells us how to fix the probability. See that? That's what this theorem does. It tells me there is a way to change the probability. There's a unique way to change the probability. Well, there's a unique way if markets are complete. Okay? There's a unique way to change the probabilities so that your wrong probabilities are right. Your 50% becomes a third. And your 50% down becomes 2/3. And that's going to be true. I don't care how many derivatives I have and what payoffs they have. That's what the fundamental theorem of asset pricing is telling us. You see? It's very powerful. It's very powerful. We will see. And in fact, it goes beyond. There's something here that says, if there is no arbitrage, then pi is always positive. If there is no arbitrage, pi is always positive. Well, ours is certainly positive, so there was no arbitrage, right? Yes? But I'm not going to ask you to do this because I know you are a little bit tired now and you need to go home. But I'll tell you one thing. Remember when Cheryl wanted to charge me 70% interest, the bond price was, sorry. We said, remember this, we said earlier today that if we insist in paying 50 cents for the option, then interest rates are 70%, logarithm of 2. We showed that calculation earlier, right? Yes? Okay. Someone who's fresh, can we calculate this pi in that situation when the option is a half? Okay. According to this theorem, it should exist, right? If the option is a half, or in other words, if my bond is a 70% interest rate, whatever that is. Okay, I'll tell you. I'm not going to do it. I'll just tell you. In that case, of a logarithm of 2 interest rates, the pi is some number here, I forgot, and 0 here. What does that mean? According to this, there's an arbitrage opportunity. Happens to be a weak one. It's not a strong one, but it's a weak one. Who can find it for me? If the option is 50%, not only we showed it earlier, right? I was making money all the time, right? I was able to, but that's when interest rates were 0. If we try to play that and I go to Cheryl and she wants to charge me 70% interest rate, maybe I cannot make it happen. Can someone tell me an arbitrage opportunity if the option is a half? How about this? You pay a half, right? Interest rates are whatever. You pay a half. I buy with your money half a stock. I'm not borrowing, you're too expensive. You see what I'm saying? I buy half a stock. What happens? If the stock goes up, I have $1, I give it to you. If it goes down, I have 25 cents and I keep. So when interest rates are 25%, I have an arbitrage opportunity. And it actually shows up here because, well, you can do it too tired now, okay? But that is 0. This pi random variable, this is called the state price deflator. That's the word, okay? This tells me if there is an arbitrage opportunity. So if you have a way to calculate these things, you have your Python code and you can solve for all the matrices in real time and say, whoops, have an alert, put an alert on your code. If there's a pi which is 0 or negative, quickly do a trade because there's an arbitrage opportunity. This does that for you too. Okay, so that's pretty neat. It's pretty neat. Now I'm thinking, I think I'm not going to prove the theorem for you now. I'll prove it next time. How's that? Yeah? Okay, I'll prove it next time. I think that's what comes after. But we did something interesting today, don't you think? We priced a lot of things, and we developed a framework to understand what prices are. Okay? All right. So we end here. I do have to run. I told you I have to get out the door. And but then we meet on Zoom next week. I'll probably show this proof to you. It'll take me a few minutes. And then we'll see what other things we can do now that we've learned this, okay?